Hello environmental assessment students. Well, this is a brief video session hopefully to give you some pre-lab instructions about our session on sampling. So we'll go through different types of sampling, but also show you the basics of a procedure to calculate the variability of a particular parameter with distance, which is something to give us information to decide on intersample distance, and that's the procedure of calculating semivariograms. So that's what we have for you today. When we talk about sampling, really we're in the position where we have to take a limited amount of information to make some inferences about the population or the wider environment in which we're sampling from. So obviously we can't sample everything, and the key feature of sampling is that it should be as representative as possible of the population, and that depends on how the sample is selected, and that's some information from Peterson and Calvin's chapter, which is on LMS. So the issues that we need to deal with, of course, are whether our sample area is homogeneous or heterogeneous in time and space, and most often the case is that it's heterogeneous, means it changes with respect to time and it's not the same at all points in space. So our sampling design would have to, in that case, reflect those properties. There are a few different types of sampling strategies. We can use judgment sampling, but this is something we're going to try and steer everybody away from. We can select what might be a typical site to represent an area, and that involves some preconceived idea about what is representative. So a conceptual model, for example, does rely on experience, and it's biased because we think we know where the best place to take a sample to represent a particular environment is. Now, that's not to say that having a conceptual model or some ideas about where to sample is wrong, but if we use that to take only a few samples to represent a whole area, it doesn't actually work very well. So we tend to use other types of sampling which are less biased. So random sampling is not biased. So if we, for example, select an area, and the graph at the top right there represents a square area where we choose the coordinates just by random number generation, it's certainly unbiased. There's no apparent human effect involved in the choice of sample spots, but as I'll show you later, it can be a little problematic. There are different ways that we can do it too. So we could use, for example, a gridded random sampling where we divide our sampling area up into sub areas and sample randomly within those and put the same number of samples or a chosen number of samples within each grid square. Stratified random sampling is quite common with the type of work that we're doing. So what we need to do is make inferences about the properties of our area, and that may be based on pre-existing information. For example, the graph at bottom right there, or a map, shows what the map of soil mapping units or soil types might be over a particular area, and so we can infer that the properties of the soil will be different or expected to be different in each of those mapped zones, and so we can sample in some cases randomly or systematically within those areas, and what it will allow us then to do is to make statistical inference about the subpopulations, and it can increase sampling precision, meaning we get a less of a spread of values because we're accounting for some of the variability that pre-exists across the site. Okay, I just want to think about random sampling. You can see that if we generate coordinates by using a random number generator, we get a haphazard or random distribution. And the problem with doing that, or one of the problems with doing that, is that we may then have areas within that area which we miss by our sampling, simply because that's possibility with random number generation. Now, gridded random sampling, and depending on the size of the grid, can avoid that feature to some extent, and it really then means that we need to make a choice about grid size, and that may be informed by the expected size of the features that we're trying to see. They may be contamination hotspots, for example, so that we can see, if we give them all the same symbol, that we're less likely to have large gaps with a gridded random sampling approach compared with a completely random sampling approach. So that may be a strategy that we'd want to use. The other main strategy that we'd use in environmental studies is some sort of systematic sampling. I mean, there's some geometric, give or take, arrangement of sampling points, and the most common one of those would be a regular grid. We can think of different implementations of grid sampling. We might want to start each column of points, for example, in this example, at alternating points, so that we get still a regular arrangement, but no longer a square grid, more of a triangular grid in this instance, and that for some applications may be a better way to do systematic sampling. We may actually want to start each transect in our grid at a random point, shown by this example at top right, or we can apply a little bit of noise to each point so that we generate a grid which has samples which are not aligned in the vertical or horizontal direction, or random cluster sampling or simple random sampling. So those are possibilities as well. But again, the grid spacing is important because we don't want to miss any features, but in the real world we have to pay for analysis of each sample, so we don't want to take too many and have them too closely spaced. So there's a compromise that needs to be made, and part of what we'll be doing in this prac session is to figure out how we might estimate the grid spacing by a couple of different ways. Okay, composite samples in some cases can be useful. It's a cost-saving thing, and it can give us quite a good way to spatially or temporally, that's time averaging of samples, but all it can do is provide an estimate of the mean, so we don't get a measure of variation. So a composite sample means, for instance, that we, in a stream or a water body, we might take several samples across a pond or a lake and combine them and then analyse the combined sample, or in a stream we might take samples at different times during the day and combine them to get a daily average, for example. So we composite them, we combine the samples into a single sample. We do miss some information in that point. Temporal sampling means that we do a time series. So we look at how a particular parameter, which might be water quality, for example, or seasonal change in vegetation, on a time basis, and that can capture some features of the data, of course, that we'll miss if we only sample at one time. Now, the number of samples that we need to achieve a desired level of precision, or a confidence interval, so a spread about the mean value, is something that we can calculate with statistical mathematics, and that the equations are quite well defined. This material is taken from Peterson and Calvin's chapter, but there's many other places you can find things like this. So what we can do is calculate the number of samples that we need to be within a particular threshold of the population mean. So it involves some assumptions about the nature of the distribution. So we calculate a z-score, and these things are tabulated in statistical tables, or you can calculate them using a spreadsheet program like Excel. So, for example, at a 95% confidence level, or a 0.05% probability, the z-score is 1.96, meaning that it's about 2 standard deviations away from the mean. And the population variance, which is something that we need to estimate because we don't always know in advance, contributes to that as well. And the allowable deviation, x minus mu, which is in the vertical lines means the absolute value of that deviation, is something that we can put in as a single number. All right. So if our deviation is 5%, for example, that we're happy with, then we make this term on the bottom of the equation 0.05 squared. Right. in order to make that calculation, we need to assume that samples are independent, and they're not always independent, and that we need to have a fairly large value of n, usually 30 or more samples, although some authors would argue for larger. So we'll do an example of that sort of calculation in the assignment that goes along with this. All right. Now, the question of independence of samples is reasonably complex, and one of the ways that we can look at it is by calculating what we call a semivariogram. This is a very common technique in geostatistics or spatial statistics, where we look at the variance, or what we call the semivariance, as a function of distance between points. So I guess there's an idea in geography and other sciences that, excuse me, we need to go back up, that if points spatially are close together, they're more likely to be related to one another than if they're separated by a long distance. So we're more likely to see independence at long distances than at close distances. And just remember, we'll go back up again, that one of the assumptions of calculating the number of samples required is that the samples are independent. So the theory of semivariance would then inform us that if points are too close together at some threshold value, then they're not going to be independent from one another. Now, we can go through this analysis, and we'll go through this step by step. It's a rather nasty looking equation at the moment, so we'll pick it apart little by little. Well, what it's telling us is that the variance between points at a certain distance is dependent on the total number of points that we have at that separation distance. So if you can imagine a grid of points across a landscape, some are 100 metres apart, and you can identify a whole range of pairs of points being 100 metres apart. We can identify a different range of pairs of points being 200 metres apart, and so on. Okay, and we need also our values of our measured parameter, so that may be density of vegetation, or it could be the concentration of some chemical in soil. It could be an count, for example, of a particular species of animal. Doesn't really matter. The form of the equation suggests that the semivariance, so gamma h, will be small when h, the distance, is small. So we'll have small variance, or conversely related points at close distances, and as we increase, ultimately we'll reach the variance for the whole data set as we increase the value of distance, or h. So let's have a look at how this might work. Right, so you can imagine that if you have a few hundred or more points spaced across a landscape, and these are real data from a study done in northern Scandinavia and northwest Russia, called the Kola area. You can see that if you can calculate the semivariance for each individual set of pairs of points, and obviously if there are hundreds of pairs of points, there are probably thousands of different possible combinations of pairs. So we got quite a messy data set, and so what's done for convenience to try and make some sense of that is to assign distance classes, and the software that we'll use, which is part of the R package, does that automatically. Alright, so we bunch up the points into different distance classes as shown by the top right plot here, and we can calculate a semivariance or show the spread of points within that. And what we then normally do is to calculate the actual semivariance by the equation. If we do it on the whole data, we get kind of a noisy but data-rich curve, but what we're generally interested in is just having a look at how the semivariance changes with distance. So what we can do is calculate the variance within each distance class and end up with the plot at lower right, where we've got a point. Each point represents a combination of semivariance and distance. And the typical behaviour of a curve like that is that it increases more steeply at short distances, and that short means different things depending on the scale of observation. Here, short might mean less than 100 kilometres. In our environment, short might mean less than 100 metres. And eventually the semivariance evens out until theoretically it becomes equal to the variance contained in the data set as a whole. And there's more reading about this in a very, very good book by Clemens Riemann and co-workers, which many chapters are on LMS. So you can go and find those and read up on this if you're unsure about anything. And just to put this in another different perspective, what we observe is an inverse relationship of correlation between points with distance. So if we look at how similar points are, that similarity decreases with distance. So we have a steeply dropping curve at small distances, which reaches pretty much zero or nearly so as the distance increases to its largest values. Alright. Now here are some examples of actual semivariograms. And what's also done is not just to have a look at the points, but to fit some sort of model to those points. And we do that because we can use the model or an equation fit to those data to calculate certain parameters. So there are some key parameters which I'm going to point out here. The first one is called the nugget. Now the nugget is basically the variance at zero distance. So that's the variability in the data that we can't get rid of even if we reduce the distance further. So it's kind of the noise in the data, and as we've seen before, the semivariance then increases to some plateau value, which we call the sill, and the sill should be equal to the population, or at least the sample variance. And the distance at which it reaches that sill is what we call the range. And so the range is the distance at which the points become independent. Now that will be different for different situations, and this is a model where the semivariance at relatively short distances reaches an actual steady value, and we can fit something called a spherical model to that, and all these are available now. Other cases, the approach is much more asymptotic than that. So we use a different type of equation, an exponential equation, to describe the change in semivariance with distance, but we can still identify those key numbers: the nugget, the variance we can't avoid, the sill, the limiting value of variance, which is equal to the sample variance, and the range. And often that will be an effective range, because with an exponential model we never actually get to a constant value. So we may define the ranges when the semivariance is 95% of the sample variance. And in some cases we might see a very, very simple relationship where it's just a linear trend between the nugget and the sill, and reaching a fixed value at the range value. Okay, so just be aware of those, just the names of those numbers in semivariance language. Okay, so what we're going to do today is you are going to construct a variogram in R using the data from the Wollongong catchment, which is data which were collected by a previous incarnation of this class and some other classes. So they're data which are developed by students, and the Wollongong catchment is in the Perth Hills. It's one of the drinking supply catchments for Perth, and we've generated a number of data sets which you'll have a look at one of those with information about soil and vegetation density and a bunch of other things. And then we're going to use either R Commander or even Excel to estimate sample numbers based on the equations in Peterson and Calvin and some other sources, and they will form the basis of short report 1. And so all the instructions for this are present on LMS under computer-based pracs and instructions, so they won't be too difficult to find. And here are the instructions for the short report. You'll submit this on LMS, and we'll put up an LMS assignment item for you to submit the reports online. Okay, and there'll be some instructions with that about the extent of the reports and formatting and things like that. Alright, there's some reading there. Both of those are on LMS. And obviously you'll need to download the data from LMS for the Wollongong catchment as well. And there's some other reading which you may well find useful. As I mentioned already, quite a number of these are on LMS already. Well, I think that's about all we need in terms of background for this, and we'll have another video clip showing you how to actually run the semivariogram procedure using R and R Commander.